In this video, we discuss exercise 102 from section 5.5 of the Larson Calculus text, 10th edition. And this problem is about breaking strength in tons of steel cables of various diameters, D in inches. So we're given these breaking strengths in tons and the corresponding diameters, and it's in a table of values, and that table of values is listed with the exercise in the text. We're going to do most of this on desmos.com. So what I will do is show you how to create that table, or just how to enter the values into the table so that Desmos will graph that data for us, and then we will fit a curve to that data. Okay, so this is our data. Now, if you're wondering how I entered that data in the table, all I did was I created a new cell here. Then I selected the plus sign for add item, and then I selected table from the list. And then I wanted my first variable to be D for diameter, but I added a subscript 1 so that I could use that D for diameter in the function that I'm defining later. And then I wanted the corresponding breaking strength for that breaking strength that's associated with that particular diameter to be represented by B sub 1. So in the table or in the textbook, it gave me this list of diameters. It said when the diameter is 0.5, the breaking strength, or 0.5 inches, the breaking strength is 9.85 tons. And then it gave me a breaking strength for a diameter of 0.75 inches. It gave me the breaking strength was 21.8 tons. And in this way, I just populated the table. So we have 0.5, 0.75, and then we increment by 0.25. Desmos recognized that that's what it was doing. So if I just hit enter a bunch of times, I can come up with all of those values in the list. And the largest value in the list in the table in the text goes up to 1.75. And then the corresponding breaking strengths varied. So I had to type those myself. So that's what I did to enter the data on Desmos. I just changed the X and the Y to D1 and B1. And then if we want to graph it, we just select this little circle here, and it'll graph the points. Now, parts A and B are pretty much taken care of. Part A says, use the regression capabilities of a graphing utility to fit an exponential model to the data, and use a graphing utility to plot the data and graph the model. So as soon as we entered that data in the table, once we selected that point, or that little like circle with the little points in it, it graphed our data for us. Now, if your domain and range aren't what they need to be, one of the things that I did was I looked at this list and I said the lowest B value, lowest breaking strength is this 9.85, and the highest breaking strength is 114. So I said, what types of Y values do I need? Well, the Y values need to be between 10 and 120. So I think I actually originally started with something like, let's let Y go between -20 and 150. And so I graphed that. And then I knew my D values had to be between 0.5 inches and 1.75 inches. And so this is actually automatically generating this for us, going from 0 inches approximately. And there's a little bit of like negative at probably -0.4 for our D value, all the way up to like approximately 3.5. But the data in our table only goes up to 1.75. So I might say, let's let our X values go from that -0.4-ish number to, let's say, 2.5. If I do that, then that's my data. And again, the highest value of D, or the diameter of those steel cables that we're talking about, is 1.75 inches. Okay, so those are our points. And we want to use the regression capabilities of a graphing utility to fit an exponential model to the data. So basically what I was looking for is a model like a to the x, essentially. But I don't necessarily just want a to the x. I might need to take that exponential function and multiply it by an extra constant to either stretch it vertically or shrink it vertically. And then I might need to add or subtract a constant to change that horizontal asymptote, we know that a to the x or e to the x, they have the horizontal asymptote y equals 0. It might be best to have a horizontal asymptote that's have a horizontal asymptote that's not equal to 0. So actually, I didn't think of the horizontal asymptote at first. I said, let's just use an a to the x type model and then multiply by an extra constant to stretch it vertically or stretch or shrink it vertically. And this is what I got. And then this r squared is 0.9844. And what that told me, or what that tells me, is that it's close to 1, so that's pretty good. But when I graph this model with the horizontal asymptote at y equals 0, I noticed that my function doesn't pass through all of the points. It's not as it's not as good of a fit as I would have liked. I would really prefer a model that passes through the points, or at least gets closer to these points than this curve does. Like we missed the point at 0.5. There's a large error there. And we missed the point at 1.25. There's a bit of an error there as well. And at 1.5. So I might say, okay, well, let's change the horizontal asymptote. Let's add a c. And that will change the horizontal asymptote. When I do that, notice that my exponential function now passes through pretty much all of the points. The error is very small for all of these values. Now our r squared, which from what I understand is a proportion of the variance in the dependent variable, that's our breaking strength, that is due to variance in the independent variable, that's our diameter, is 0.9998. So that's really, really close to 1. We want it to be as close to 1 as possible. And that's pretty good. So we're satisfied with that. So what this did was I said to Desmos essentially, I want you to associate those values B1 in my table with a model like this. And I want you to find the value of lowercase b and the value of a and the value of c so that this exponential model is the best fit possible for these data. And when I say best fit, basically we're minimizing the sum of the squared errors. So you look at the difference between the y values in the model, or the b values from the model, and then the b values that we have from our table, from the data set. And you want to take those errors and you want to square them. And then you want to make that sum of squared errors for all of those data points as small as possible. And if you do that, that will basically select the right values of A, B, and C so that this model fits through the points, minimizing that error. And it turns out we were able to do that. The B value that we need is that 37.3247. The A value, that's our base, is 2.31274. We're raising that to the D power, where D is the diameter of that steel cable. And then we're subtracting 47.5254. Now, if I wanted to just type that function now, I could say, let's let B be a function of B. And I want my B value, my sort of vertical scaling value to be 37.3247. And I'm going to take 37.3247 and multiply by A, that's 2.31274, raised to the D power, where D is the diameter of the cable, minus 47.5254. If I graph that function, we'll see it's the same as the model that we have right there. And again, the A, B, and C were selected to minimize the distance between the B values from our table and the B values that would be given by the model. In some sense, we take the error between those two values, we square it, we add them, and we want to minimize that sum of the squared errors. And now we see that our new horizontal asymptote, rather than being y equals 0, which is what it would be if I didn't have that c there, which is associated with a smaller r squared value, which means that the model is not very good, or it's not as good as the other one is. If I add that c, asymptote, instead of being y equals 0 like it was for this one, is going to be y equals c, where c is that negative 47.5-ish number. So if I graph that horizontal line, this is what we have. And if I zoom out a little bit, we can see we've got that exponential type curve with the appropriate horizontal asymptote. It really fits through the data. It looks like it fits through all the points. So it's pretty nice. Okay. That's parts A and B. Now, we did not have to use an exponential model, although that's what we were asked to do. We were asked to fit an exponential model to the data. If we wanted, we could have fit a different model. We could have said, that kind of looks like a parabola. Let's find a function of the form ax squared or ad squared plus bd plus c. Or let's find a model of the form, you know, like a constant times x squared plus a constant, you know, something like that. It does sort of look maybe quadratic, or maybe I could say maybe it's not just quadratic. Maybe it's a polynomial. Maybe it's a third degree polynomial. And then we could say I want my b value to be a d cubed plus b d squared plus cd plus not d. We'll have to use a different letter. Let's say e. And of course, we're not talking about the natural base, but you know, just another constant. And the regression capabilities of this Desmos graphing calculator would find the values of the coefficients that would minimize the squared error. Okay, so we've got this. This is our function. Looks pretty good. Now we're asked to find the rates of growth of the model when d equals 0.8 inches and when d equals 1.5 inches. So basically, we are just differentiating this function with respect to d. And I just typed in A, B, and C so that we could see the values of A, B, and C. I also typed the A, B, and C in here so we can see that function explicitly with A, B, and C substituted. But in general, we can just type it this way, where B is this constant, C is that constant, A is that constant. Say, okay, well, what's the derivative of this function with respect to D? Well, this constant just comes down, and then the derivative of a to the d with respect to d is just like the derivative of a to the x. So we're going to have natural log of the base, which is natural log of a, times the exact same exponential, which is a to the d in this case. I know it looks a little weird because d is our independent variable, and usually we're used to x being the independent variable or t being the independent variable. But d stands for diameter. And so you just have to remember that you're differentiating with respect to that particular variable. And of course, the derivative of the constant is 0. So b prime looks like that. And if we evaluate that at 0.8, we get 61.2. And if you're saying, well, what is that? Well, remember what b prime is. B prime is db dd. And these lowercase d's in the front are related to the differentiation operator, the Leibniz notation, and the second d there represents that diameter. So we're saying, what is the instantaneous change in breaking strength with respect to diameter when the diameter is 0.8 inches? When we evaluate that b prime at 0.8, we get that 61.2. Well, that's going to be in units of tons per inch, because that b prime is the instantaneous change in the breaking strength, which is in tons, per inch, which is the units of measure for our diameter. So when we get this 61.2 number, we say the breaking strength is increasing because it's positive at a rate of 61.2 tons per inch when the diameter of the cable is 0.8 inches. That's what that says. Now, if we wanted to, we could plot that point. It says I'm defining B in more than one place. It doesn't like that. So this orange point that I've just plotted is not a given data point. It is a point on the curve for our model. Like our given data starts at, what was it? 0.5 inches, and then it increments by 0.25 inches. So we've got data for 0.5, 0.75, 1, 1.25, 1.5, 1.75. But we don't have any data for 0.8 inches. But if we use our model to approximate what the breaking strength should be for a steel cable with diameter of 0.8 inches, our model tells us that the breaking strength should be 24.47 tons approximately. Now, at that instant, when the diameter is 0.8 inches and the breaking strength is that 24.47 or 25.47 tons, then the rate of change of that breaking strength with respect to the diameter is 61.2. So that means the breaking strength increases by 61.2 tons per inch when the diameter of the cable is 0.8 inches. Now we are also asked to evaluate B prime at 1.5 inches. So you just substitute 1.5 into your B prime function, and we got 110.07 approximately. So that's just telling us that the breaking strength at that point is increasing at a rate of 110 tons per inch when the diameter is 1.5 inches. So again, if we wanted to, we could plot that point on the curve. Now we actually have a breaking strength for 1.5 inches already. We have a data point for that. But this orange point is not using the data. It's actually using the function itself. So it's plugging in 1.5 to that approximation that's relating the breaking strength of the cable to the diameter of the cable. And you say, okay, well, what is B prime at that location? It's 110.07 approximately. So the breaking strength is 110 tons per inch when the diameter of the cable is 1.5 inches. All right, that's cool. We had rates of change. We've got some modeling and some curve fitting. And that's pretty much it for that problem. If you want to, you could also graph the tangent lines. You don't have to, but I always like to graph the tangent lines. Say y equals B evaluated at 0.8 plus B prime evaluated at 0.8 times D minus 0.8. And you can see this is a linear approximation of the breaking strength when we're close to 0.8 inches. I'm going to try to get rid of those labels now. And we can use this linear approximation to approximate the breaking strength as long as our diameter is close to 0.8 inches. And we could do the same thing at 1.5 inches as well if we wanted to. Just instead of evaluating the breaking strength function at 0.8, we evaluate it at 1.5. And then we get the tangent line at that location. And of course, the slope of these tangent lines is given by the y values on this purple graph, where the purple graph is the graph of B prime, or the instantaneous change in breaking strength with respect to that diameter. I actually don't know much about this application. Obviously, I've never really thought about breaking strengths of steel cables in terms of diameters. I hope that this real world application is actually a real world application. I just got it out of the book. But that is how we use Desmos to get a function that has a particular form. We say, okay, I want an exponential function, so I want a to the x essentially. But instead of using x, I'm going to call the independent variable d. Instead of using y, I'm going to call the dependent variable b. B for breaking strength and d for diameter. And then I say, okay, I don't just want a to the x. I might want a to the x multiplied by a constant so that we can stretch it vertically or shrink it vertically. Then I might want to add or subtract some constant c to move that graph up or down. And so I just told Desmos that that was the form I wanted. And I said, please find A, B, and C so that this form sort of fits my data. And then you say, how does it fit the data? Well, we want to choose A, B, and C to minimize the sum of the squares of the errors, and the error is the distance between the B value given by the model and the B values in the table of values that we have. So Desmos does all of that work for us. All we have to do is put that tilde there and ask it to find a model of this form, and then it finds the model of that form with coefficients or with sort of unknowns A, B, and C. It gives us the A, B, and C, and then it tells us what that R squared is. And if that R squared is close to 1, that means that sum of the squared errors is well, very small. It fits really well if that R squared is close to 1. And this is a measure of the proportion of the variance in the breaking strength variable that is due to the diameter. That's my understanding. And we want that to be as close to 1 as possible. So that is that. Can't think of anything else to add. Let me know if you have any questions about it.